Today let's do Laboratory 1-3D, where we're going to measure the power transmitted from a helium neon laser through various colored filters. The setup for this laboratory is quite simple. We'll just direct the laser beam straight into the power meter and insert into the path of the beam various colored filters and take our measurements. So let's get to it. Alright, so we've got our beam lined up with our photodetector, and you can see that our incident beam has an input power of 0.79 microwatts, which with the 1,000 to 1 attenuator would tell us that we have 0.79 milliwatts. Now let's put the blue filter in place, being careful to not reflect anything onto any neighbors. And now you'll see that the power drops down radically to 0.01 microwatts, with the 1,000 to 1 attenuator would be 0.01 milliwatts. So we will record that data in our data table. Alright, now I'm ready with my yellow filter, and you'll notice that the incident beam is now registering 0.81 milliwatts. It's gone up a little bit, and I'll position the yellow filter in place, and the power drops to 0.70 milliwatts. And I'll record those two values in my data table. Alright, now we're ready to try the green filter. Our incident power is back to 0.80 milliwatts, and our transmitted power drops to 0.05 milliwatts. So we'll record those numbers into our data table. And lastly, we have the red filter, and we'll see that the power incident on this filter is going to be 0.80 milliwatts, and we put the red filter in place, and we have a transmitted power of 0.68 milliwatts, and we'll record that into our data table. Okay, well, let's crank through some of the calculations for this first part of this lab. Here are the data measurements that we collected for the blue, yellow, green, and red filters, the power in, the power out. And so let's calculate the transmittance for the blue filter, for example. The transmittance would be the power out divided by the power in, and that calculation would give us 0.013, or 1.3% transmittance, not very much. And the OD calculation would be the log of that number. The negative of the log base 10 of that number would come out to be 1.9. Almost very good for blocking red helium neon laser light. And just for a comparison, let's look at the red filter. It transmitted quite a bit of the red laser light, and it had a divided 0.68 by 0.8 incident, and we have a transmittance of 0.85, or we transmitted about 85% of the laser light at the red filter. And the OD value for the optical density of the red filter would be the log of this 0.85 value would be 0.07. And so that has very little optical density value at the red laser light. Alright, so let's go on to the next part of this lab. For the second part of the lab, we're going to look at the effect of the two filters as the laser beam passes through. And so we've got a setup here where we can bring one filter into play and then the second filter into play. The power incident on both of these filters we can see is 0.81 milliwatts. So we're going to bring it through first a yellow filter and then the green filter, and the result is 0.05 milliwatts. So you can write that value down in our data table. And the next step would be the green and the red. Incident power is 0.81. So we'll place the red filter in place and the green filter, lower it into place. And we read 0.05 milliwatts. And because it's easy enough to do, let's just simply hold the yellow filter in place for the finally, and we'll see that the power drops to 0.04 milliwatts. Okay, so here are the data values that we recorded for our multiple filters of green and yellow, power in and power out, green and red, and green and red and yellow. Let's go through the calculations for the first one just as an example so you can see how to do the rest of them. As before, the transmittance is calculated by dividing the power out by the power in. So 0.05 divided by 0.81 for the green and yellow would give us a transmittance of 0.062, or about 6.2%. The predicted transmittance would be the combination or the product of the green transmittance and the yellow transmittance, which from our previous experiment would be 0.0625 times 0.864. If you multiply those two numbers, you'll get 0.054. And if you calculate the percent difference between those two numbers, that would be 0.062 minus 0.054 divided by 0.054. You'll get a percent difference of about 15%, which is not too bad for our calculations. And you can do the rest of those calculations yourself for the other combinations of filters. All right, this lab asks us to measure the thickness of these filters with a micrometer. And so we have our micrometer here, and Derek is putting it into position and measuring it very carefully.
So we got 1.8 thousandths.
1.8 thousandths for the blue filter. Okay, so we'll write that down in our data table, and Derek's going to go ahead and measure the rest of those filters, and you'll do the same. Now that Derek has taken all of the thickness measurements, we can put those into our table. So here's a representation of table 3 in the lab. For the blue filter, he measured 0.00457 centimeters, if we convert his measurements in thousandths of an inch to centimeters. And similarly, you can see the readings we got for the yellow, green, and red filters. First, we'll need to calculate the transmittance, the corrected value. From your table 1, you measured a transmittance of about 1.2% or 1.3%, not very much for the blue filter. If we correct that for the Fresnel reflection, as the text indicates, we need to divide that measured transmittance by the quantity of 1 minus r squared, where r is that reflectance that happens, which is 1 minus the index of refraction divided by 1 plus the index of refraction, all squared. So to do that, we're going to use the 1.499 for the refractive index of our plastic filters, probably an approximation, but it'll be close enough for the exercise here. And if you use that formula, you'll come out with a corrected transmittance. Instead of 1.3%, we'll come about 1.4%, which is 0.137. And you should be able to reproduce that calculation by using the method I just described. Similarly, for the yellow, we'll get 0.937, about 94% transmittance for the yellow filter. Much different than the blue, isn't it? And about 0.678 for the green filter and 0.922 for the red filter. Now we need to calculate the absorption coefficient that corresponds to these transmittances. And to do that, the text indicates that you need to use the negative log of the transmittance divided by the thickness of the filter. So, for example, for the blue filter, we'll plug in minus log of 0.0137 and then divide that by the thickness of 0.00457, and we'll come up with an absorption coefficient of 938 per centimeter. All right. How does that compare with the yellow filter? Well, if we do that same negative log of 0.937 divided by the thickness of our yellow filter, we'll get an absorption coefficient of about 8.5 per centimeter. Big difference in the absorption that takes place using a yellow filter and the blue filter. And you can do the similar calculation for the green and the red filters. I hope you've learned a little bit about how the colored filters absorb the light from a laser in this lab. And we'll see you next time for the next lab in Fundamentals of Light and Lasers.